Hi one and all. Today I am here about Tech Talk presentation. My name is Steven from Aeronautical Department. My topic is the Painlev E-paradox in contact mechanics. And let's go into the topic. And let's know your introduction and historical perspective, general formulation for planar resolution of paradoxes via contact regularization, multiple contact points, single point of contact, and discussion. And let's go into the introduction. Paul Painlev is a truly remarkable figure in the history of science and technology. In mathematics, Painlev is the most closely associated with the family of integrable differential equations and corresponding transcendental functions that bear his name. But there is much more to Painlev. He made pivotal contributions to the theory of gravitation. He was possibly the first ever aircraft passenger taking a seat in the Wright brothers plane in 1908 and set up the world's first degree in program in aerospace engineering. Historical perspective. The classical Painlev problem, the CPP, first proposed by Painlev in 1905, involves a slender, rigid rod falling under gravity while in contact with a rigid, stationary, frictional horizontal surface. Suppose the rod has mass m and radius of gyration, or that the center of mass is a distance from the contact point P, and that lambda n less than or equal to 0 and lambda t are the normal and tangential components of contact force. That makes the normal acceleration in vanish so that the rod remains in contact while it falls. Similarly, if theta is initially small and positive so that the rod is close to horizontal, then B greater than 0 and P plus less than 0. However, for intermediate angles, depending on other parameters and velocities, P plus and B may in general take either sign. So let us analyze what happens at a time when either P or B smoothly changes sign during motion. Is a paradox due to unrealistic friction models. One simple possible resolution of the Painlev paradox is that a coefficient of friction mu is equal to 4/3 is unrealistically large, with typical values for most materials being significantly less than 1. This resolution is spacious though, because it is very easy to formulate mechanism for which mu p minute is significantly smaller. For example, if we allow the rod in the CPP to be non-uniform, then mu p minute is a function of the radius of gyration, or taking the limit that all the mass is concentrated at the center of mass, then R to 0, and the formula shows that mu p minute becomes vanishingly small in this limit. Another possible resolution is that the Coulomb friction law is too simplistic and that if a more realistic friction model is used, the Painlev effect will disappear. This may be possible for certain cases and configurations, but seems unlikely in general. For example, Lee et al. Find the paradox to still be present in a model that has a different dynamic and static coefficient of friction. In addition, there is a trivial indeterminacy if, as is typical for such models, the static coefficient of friction is higher than the dynamic one. And next, in the limit that the slope tends to infinity, also Ivanov claims that such friction laws introduce further non-uniqueness in place of non-extensions. If instead we replace Coulomb law with a Steinbeck law, in which there is still a jump at u is equal 0, but it is taken to be smooth function of u. Then the above calculations for the CPP can be easily repeated. It is straightforward to show that in principle, there is no impediment to p plus becoming negative in this case too. The same conclusion holds if it is a function of position x, q are some internal state variables such as in rate and state friction models. Other mechanical configurations. In fact, as pointed out by Lene et al., the original problem studied by Painleves in 1895 was not the CPP, but that of a planar box slipping down a rough plane that is inclined at a shallow angle to the horizontal. The box is assumed to be in point contact as its lower corner and to be subjected to Coulomb friction. As Lenin et al. Show, the simplest model of its problem is actually dynamically equivalent to the CPP. As mentioned in the introduction, the motion of chalk being pushed across a blackboard is often proposed as a classroom illustration of the Painleves paradox. In particular, if the chalk is dragged, which would correspond to an angle theta, is the second quadrant if motion is to the right, then a uniform straight line is generally seen. Next, look at the picture. Despite the chalk being pressed into the board, such as explanation is not sufficient, however, because the coefficient of friction for chalk on a blackboard is likely to be significantly less than mu p min is equal 4/3. However, the contact mechanics of chalk, a cylinder that is typically only in contact element part of it tends, it likely to be more complex than that of an ideal rod. And we also have to talk account of the body forces and controls being applied by the teacher. Moreover, we shall also see in seconds. There are also possible applications of these ideas in biomimicry of sensing system. For example, mammals such as rats have slender trapped rod like fissures that repeatedly sweeps and turn on a surface. Oblique angles. It would appear that the combined effects of stick slip and lift off from the tip feedback along the whisker enable the rat to sense both texture and compliance of the surface. Various attempts, regularization and impact mechanics. Various attempts to resolve the Painleves paradox have taken place in the intervening 120 years since Painleves first published this work. These attempts took on new vigor in the 1990s due to the development of rigorous methods using the complementary framework for rigid body mechanics and the theory of differential inclusions. And next, general form for the single contact case. This section is divided to the answering questions. Restricted case of planar surface with a single point of contact without introducing any additional ingredients to the rigid body formulation. We shall deal with typical cases given by open conditions on parameters. Cases that are on the boundary of these open regions are dealt with in seconds. Consistency of contact motion. Sustained contact occurs when y is equal v is equal 0, from which we can distinguish 4 generic possible nodes of motion: lift off into free motion f, stick t, and slip either in the positive u s plus or negative u s minus direction. Here, to determine which mode is consistent for any conformation, we can apply 3 steps of algorithm. First one, check kinematic admissibility. Second one, find contact forces and accelerations using equations of motion and equality constants. And third one, check constancy conditions. Let us now consider the details of the constancy analysis for the 4 contact modes. And impact. The discussion of Painleves paradox is a rigid body framework requires the inclusion of an impact law. If contact regularization is included in the normal direction, the necessity of IWC is easily concluded. This phenomenon occurs in parameter region 7 to 10 of the figure, which occurs when one of the parameters k plus or k minus is negative. And next, chattering and invert chattering. Chattering, also known as Zeno phenomena, is a process by which an infinite sequence of impact occurs in a finite period of time. In single degree of freedom, mechanical system such as sequence can easily occur whenever there is a coefficient of restitution less than unity and acceleration that is towards the contact for a sufficiently long period of time. The canonical example of such an impact sequence occurs when dropping an elastic ball on a rigid floor and can also occur in general impact oscillators. For systems with oblique impact, shattering sequence can also convert in reverse time. In case E less than 1 gives a possibility of reverse chattering sequence defined by the bounds mapping convergence as n2 minus infinity, we would have an infinite sequence of increasing bounces that starts at some time t0 with zero displacement and an arbitrary phase. This arbitrary constant get multiplied by a factor E less than 1 at each bounce, so that at an 0-1 time later there is a continuum or different possible solution separated in phase by the finite time interval Tn given by since Tn to 0 as n2 minus infinity. In this case, we find that trajectories for all these different phases emerge from the same initial conditions. Note that is not necessary conditions that we are Payload region. In particular panel, we illustrate the condition for E less than 1 for the CPP, and a reverse shatter can be triggered all the way down to mu is equal to 0 in the case of perfectly elastic collisions r is equal to 1. And next, stability. Most forms of motion within rigid body systems with contact can be described by special solutions, often appropriately defined by dynamical system. In order to understand which of these motions may be observed in practice, it is common to examine the stability of these solutions. There are, however, several notations of stability in dynamical systems, and the choice of an appropriate definition is made more subtle by the presence of unilateral constraints. The simplest kind of motion is equilibrium. Equilibrium conformation is contact only exists if every contact is in stick. We shall consider the case multiple contact point. For the present, we shall confine ourselves to conformations with a single point of contact. One characterization of stability of an equilibrium in stick contact is that the system should resist small variation of external. 3 points. The curvature of the object and the contact surface must tend to the local minimum of the potential energy of external forces along trajectories within stick. If this criterion is not met, divergence from the equilibrium with the T mode becomes possible. The equilibrium must be unambiguous in the sense of unambiguity ensures that a system may not diverge from the equilibrium state in F, S plus or S minus modes unless it undergoes an impact. And third point, additionally, upon defining the effective restitution coefficient E for chatter then we must have E less than 1, otherwise a small perturbation may trigger diverging reverse chatter motion. Resolution of paradoxes via contact regularization. This leaves the indeterminate region. We shall now analyze this case in the sense of question 3 by adapting contact regularization, introducing of a form of finite elastic into model, and then passing to the limit that the stiff stiffness tends to infinity, there are a number of different choices that can be made. Normal stability of free fall. The free fall mode does not involve active contacts. Lambda n is equal to lambda t is equal to 0. The fact that the contact forces are 0 makes them robust against small perturbations. That is y less than 0, then small perturbations in normal forces cannot affect the motion. Alternatively, free motion can occur if y is equal to 0 and v less than 0. Here, small perturbation of normal force will not be sufficient to make v is equal to 0. Hence, the system remains in F mode in response to small perturbation, which means that we can consider the F mode to be normally stable. Normal stability of stick. Thus, upon the introduction of compliances and taking the infinite stiffness limit, a firm conclusion can be made within cells. That is, if a body is in the state of sustained stick, then this motion is stable to small perturbations in forces, and the only way to leave sticking is by reaching the boundary of the friction cone. In particular, a body that is in contact and sticking will remain in stick, even if the failure region with b less than 0 is reached, provided that the body remains inside the friction cone. Normal stability of slip. Without loss of generality, consider positive slip. Proceeding similar to above, we end up with an equation for the normal dynamic that reads d into dt is equal to 0, 1 p plus kp plus q, where k and q less than 0. Hence, there are two eigenvalues with negative real parts with p plus less than 0 and two real eigenvalues of opposite signs if p plus greater than 0. Thus, we conclude that the normal stability of the equilibrium in the Faust-Schill dynamics is determined by the sign of p plus. Thus, positive slip is stable to perturbations in the normal direction if and only if the appropriate Painlev parameters p plus is positive. Hence, forward slip is unstable in the Painlev's region p plus less than 0. A similar conclusion holds for negative slip in the case p minus less than 0. Thus, we have that no conformations can smoothly evolve slip into the Painlev region with b less than 0, as the state would be violently unstable with a normal stability. Updated contact mode consistency. In the light of the above analysis, we can update table 2 to take account of the normal stability results and the possibility of impact. The above mentioned indeterminacy between lift-off and impact occurs in cells. There is also another indeterminacy in cells, and where either stick or lift-off can occur, which we shall explain shortly. Triggered transitions between states. In this session, we focus namely that are generic ways in which a conformation can enter a Painlev region, and what must was then happen. Theoretically, there are only two ways of reaching sustained contact in a Painlev state, moving from a non-Painlev contact to Painlev's contact, or establishing sustained contact via the termination of a Chataning sequence inside the Painlev remain. We deal with the two positive in the next two subsections. We shall then look at ways in which reverse chatter may be triggered while in contact. Entering a Painlev region within contact, that is G-spoke. Here both P less than plus or minus 0. If we want to know how to continue the dynamic T less than T naught, and the parameter P plus or minus and A and B will be smooth functions of time provided the body does not change if mode of motion. In particular, a change of sign of P plus or minus would not affect the mode of motion. This is not true of slip through. As we have seen, inappropriate pain loss parameter became negative, then slip changes from being highly stable to higher unstable. For the definition, let us consider a positive slip U less than 0 within region. The analysis for negative slip is similar. We are interested in where P plus being close to 0 for B greater than 0. So suppose we have an initial condition with 0 less than P plus 1 ends according to the contact force lambda n is large. Reaching a pain loss state via complete chatter. In this analysis, both stick and slip in pain loss region, assuming that the trajectory arrived in the pain loss state by smooth evolving while in contact. It sticks unaffected by either P plus or minus greater than 0, provided the body is in the interior of the friction cone. And pain loss region while slipping is via the G spot. What we have not investigated through is whether completed chatter sequence end of 0 point, that is in pain loss region, triggering reverse chatter. A final possibility for a complex trigger transition would be a body that is smoothly in contact, where the spontaneously undergoes a reverse chattering sequence. This possibility was considered by Nodmar et al., the results of which we summarize here. In general, we can rule out such as spontaneous triggering of reverse chatter in T mode by the analyzing in second. Since provided the body remains in the interior of friction cone, stick is stable and similar to the analysis of second. And multiple contact points. Let us now consider generalization of previous results to system with multiple contacts. Our aim is identify which properties of pain loss paradox are generally true, and which there are specific properties of single contact system. Moreover, we will uncover many extra forms of degenerate that are unique to multiple contact point systems. Consistency analysis of contact modes. To begin with, consider a planar rigid body system that has 2 points contacts with non-zero tangential velocities. Xi is equal y is equal to vi is equal to 0, and ui less than 0 for I is equal to 1, 2. And here there are four kinematically admissible nodes. There are S plus and S plus and S plus F, Fs plus and Ff. Here the two letters symbols refer to the specific combination of modes, two contacts. The two contact forces accelerations are determined with the help of equality for both contacts. A contact mode is demand constant if the constancy conditions satisfied were both contacts. And here contact regularization and stability analysis. To resolve the indetermination cases, we can compute the normal stability of different points of contact by the method induced, that is induced a contact regularization in the normal direction. Linearize the ensuing equations of motion, perform an eigenvalues analysis on the appropriate Jacobian matrix, and then pass to the infinite stiffness limit. And here impacts without collision. Let's now consider the possibility of impact, specifically an IWC for each of the cases and methods. Look at the picture, and there are gravity and direction of slide C and musical 0.6, and take a minute in this picture. And next, single point of contact case in 3D. Everything discussed so has been for systems whose contact forces and motions line in a plane. Much less is known about the Penrose paradox in situations that require a fully three-dimensional analysis. For simplicity, we restrict attention to the single contactees. Our goal is to highlight similarities with and differences for the planar case. In what follows, we make some general observations, but only do precise calculations in the case of three-dimensional analog of the CPP. And finally, we are into the discussion. We are discussing about Penrose. This article represents an attempt to survey the state of knowledge on a range complex phenomenon in rigid body mechanics that have been grouped together under the epithet of the Penrose paradox. We have done particular attention to recent results by the authors and their collaborators, while trying to establish some general notations and terminology that we hope will help to organize the previous literature and stimulate other researchers to investigate this fascinating topic. Let us close with some philosophical remarks and a brief summary of open problems. And finally, I'm saying here thank you. Thank you for giving this opportunity.